Hi, everyone. I think we'll wait a couple more minutes for everybody to come on in and we'll get started. All right, I think we can get started, and if there are any further attendees, they can join us as we go along. So a quick reminder to everyone. So while the presentation is ongoing, keep your video switched off and turn your video on, or put a message in the chat to let me know that you'd like to ask a question. And so long as you'd like to make follow-up points, just leave your video on and ask your follow-up questions. And of course, if you either don't have access to a webcam or would rather not use one, you can use the little hand raising reaction in Zoom, and your icon will pop up for me. So I'll be able to see that you would like to ask a question. So I know that this month we were supposed to hear from Sabri and Florian about Ferrocene, but we've decided to switch the dates up a little bit. So they'll be giving their talk in April, and I'm instead giving my talk today. And then next month we have, I'm sorry, I should have corrected this in the schedule. We have a talk about what used to be called the Rust model checker, and it's now called Connie, I believe, or, if I'm not getting it wrong. But it's a model checker being developed for Rust at Amazon. And so we'll hear from Selena and Daniel in March about that. And then, of course, we are always looking for more presentations. So if you'd like to talk and share your work, for example, we have a slot in May. So just reach out to me either on Zulip, through the formal Ferris Twitter, or by email. You can find my email rather quickly. So I guess we can get into things. So today I'll be talking a little bit about my personal work on Rust verification, which is a tool I've been developing called Creusot, which is a deductive verifier for Rust code. But of course, why do we care about verifying Rust code when we already have C, this fantastic language which we can already use to write safe, reliable, and portable systems level code? and makes it, which is why it's ideally suited for writing, critical software like nuclear reactors, airplanes, cars, all sorts of fun things. So as some of you who have C experience may know, of course, there are plenty of traps that we can fall into when we're reasoning about C code. I guess I can also, sorry, I just realized I didn't turn on my camera. Not that it's all that important, but so there are plenty of traps that we can fall into when we're reasoning about C code. To start off, our input could be malformed. We could easily have issues like a null pointer here, or data which is more deeply ill-formed because the C type system only provides us with very basic guarantees. And similarly, in C, of course, we can have cyclical references to our pointers, right? So we can have two pointers which point to each other, which means that simple common C idioms like using a null pointer to mark the end of a linked list will fail to terminate if we ever pass a circularly linked list to those functions. And so in this simple C list reversal code, we already have issues which betray our intuition for the behavior of these programs. Whereas, of course, when we write the same program in Rust using the strict ownership types and mutable borrows that we get, then basically the same code syntactically gives us a much stronger semantic guarantee, right? We know, for example, that our mutable borrow to a list is going to be non-null. It's going to have a well-formed list behind it. Similarly, we also know that our list is acyclic because we can't construct a circularly linked list without using clever tricks like ghost cell, which is Ralph Young's paper, or unsafe code. But at the same time, we managed to keep much of the same behavior, right? So we're still dealing with, of course, with low-level pointers and manipulating memory directly. There's no garbage collection, all the fun standard Rust guarantees. So Rust already provides us with quite a lot in the way of informal reasoning about our code, right? We can much more easily understand the behavior of our borrows, of our pointers, of our data structures, because we have an actual type system here to help us out. We also have ADTs, all this fun stuff, but we can actually, of course, lean on that same type system to help us reason formally about our code. And so that's the idea behind Creusot, and that's the idea behind Krusty as well. And a lot of Rust formal methods tools is leveraging the Rust type system to help us simplify the verification. So in this talk, of course, I'm going to be showing how Creusot works. So I'll start off by presenting a little bit of the theory behind Creusot, which is what we call the RustHorn model. It's based on comes from a tool developed by Yusuke Matsushita, who may be among us tonight, called RustHorn, which made some very clever observations about the behavior of mutable borrows and came up with a very ingenious way of representing them. And then afterwards, I'll talk a little bit about Creusot, the actual tool, the specification language that we've developed for Rust programs, and as well as, if we have time, a little bit of some of the more advanced functionalities that we can use in Creusot. And then finally, I'd like to give a little demo of the tool and the kinds of how we can verify actual Rust programs with it. So the RustHorn model. So RustHorn is a tool which verifies Rust programs by modeling them using constrained horn clauses, which are a subset of first-order logic. And the key contribution in RustHorn was this observation on how to represent mutable borrows. So what RustHorn noticed is that, of course, mutable borrows are unique. They're non-aliasing, right? So whenever we have a mutable borrow to some structure, we're guaranteed that there's no other mutable borrow that is active at the same time. And because of this property, we can use this trick of prophecies to represent mutable borrows. And it eliminates the need for all the same heavyweight tools that we usually find when dealing with imperative program verification. So we don't actually end up needing to use separation logic at all to model our safe Rust programs. We sort of boil all of that away and just leave this like core of first order logic verification conditions. And this produces verification conditions which are very, very compatible with existing SMT solvers and first order logic reasoning tools, because we've eliminated all the really tricky stuff about handling the memory, handling our heap. All that's been eliminated by this encoding. So what is this encoding? If we look at the very simple case, let's just start off by considering only boxes, right? So when we have a box, that means we have an owning pointer, right? Which means we have exclusive ownership over the contents. We don't even have the possibility of aliasing or sharing at all, right? If you have a box X of some value, there's no other way you can't for you to read for somebody to read the contents of X. Of course, this is ignoring borrowing for the moment. And so in this RustHorn model, the idea of the RustHorn model is going to be, well, we can just eliminate the boxes entirely, right? So if we on the left-hand side have this little program where we have X, which is a box that holds 5, and Y, which is a box that holds 0, we can do operations with our box Y and still know at the end that X still holds 5, right? There's no way for Y to interfere with the value of X. There's no way for any external function to interfere with the value of X. Oh, I'm sorry. Okay, so apparently my microphone has been breaking up. I'm going to attempt to switch microphones and hopefully, is this any better? Okay.
Much better.
I'm so sorry about that. Okay, well, sorry. Right. So the idea in this RustHorn model is that we're going to be leveraging the ownership typing of Rust to help simplify the verification conditions, right? And so if we start off with a simple example of boxes, as I was saying, the boxes tell us quite a lot about what's going on in the memory, right? There's no way to get sharing. There's no way to observe another box than the one we already have under our hands. And there's no way to sort of synthesize access to it. These are things that aren't typically true in a language like C, where we can have all sorts of global variables that are being mutated by a function. So we don't necessarily have a guarantee in a program like C that X hasn't been changed under our feet. It could have been that X actually was the same thing as Y, right? That they were aliased. Or it could be that we're not actually talking about a local variable X in a C program, but a global mutable variable. And so because we have all these strong guarantees from the type system in Rust, we can actually erase the boxes entirely in our translation. So we can actually just treat the values like they were functional programs. So on the right-hand side, I've written sort of the RustHorn interpretation of these programs in the form of a simple functional language. We can then turn that functional language into constraint horn clauses like they do in the RustHorn model, or in the RustHorn paper and tool, or in Creusot, where we actually do use a functional language. The two are equivalent. But of course, if we only had boxes in Rust, it wouldn't be nearly as interesting for us to use because we would have no way of actually sharing data. We would have no way of getting indirect mutations. So of course, we want some form of pointers. And in Rust, of course, we use mutable references or borrows for that. And this is the key contribution of RustHorn, is the representation of mutable borrows, which is this idea of representing a mutable borrow as a pair of values, a pair of a current value and a final value. And so the idea here is if we have some value A and we create a borrow B from A, right, for some lifetime alpha, the moment that we create B, we've transferred all the permissions of A into B, right? We can't refer to the variable A for the entire duration of the borrow. Reading and writing has to happen through B. B can, of course, recursively hand out another borrow to its contents, right? We can always take a smaller borrow out of a borrow. But for all of alpha, we're certain that the only person who can actually modify whatever was inside of A is B. This is what the Rust type system guarantees us.
So in particular, it also means that we don't actually care what's inside of A for the entire duration of alpha. We don't need to know what's inside of A because we can't observe it. All we know is that at the end of alpha, at the end of our borrow's lifetime, we're certain that whatever is in A agrees with whatever is in B. We also have the same guarantee at the beginning of the borrow, of course, right? We know that at the start of the borrow, whatever is in B is the same as what was just in A. And so this is the idea of prophecies. It's that we're going to preempt the entire borrow. We're going to just guess the final value of B. We're going to stick it directly in A the moment we create our borrow. And so this is going to help us simplify. This is going to help simplify verification quite a lot. So on this left-hand side, we have a little program where we have a mutable variable X. We create a borrow T from X. And then we're going to do some operations on T. So the interaction, sorry, we had a question from Daniel Schwartz-Narbonne about how prophecies interact with cell. The complete answer is it's still an open question. Mutable cells, of course, in Rust allow us to have mutably aliasing state. And this whole prophetic model crucially relies on not having mutably aliasing state. So it's not, we don't believe that it's possible to directly use prophecies to represent cells, but it is possible to have a different approach to translating cells that coexist with a prophetic kind of approach. And we've actually explored this a little bit, but the reality is there's still a lot of work to do on handling types with interior mutability in a prophetic model. So when we create our borrow T from X, right, we create our borrow T, we do some operations, for example, we increment it by 5, and then eventually we release our borrow. So implicitly in Rust, this is basically a drop. I know for the Rust compiler people here, that's not necessarily how it would exactly be translated, but that's the idea here. We're releasing T, right? We're getting rid of it. And afterwards, we're allowed to use X again. We've recovered our permissions to X, the borrow is ended, and we can now see that X is 5. So in our prophetic translation, what we're going to do is at the moment that we create our borrow T, we're going to guess its final value. This is represented in the right-hand side by the construct any. The construct any is going to make a non-deterministic choice for our final value. It's just going to get it. But we're immediately going to update X with this final value. So we're just going to tell X, here's what you're going to be in the future, right? And then as we do our calculations with our borrow T, we continuously increment its current value, right? So as I said before, mutable borrows are represented by this pair of values, the current and the final value. And we do all of our operations using the current value. So when we increment the value of T by 5, we just update its current value to be whatever it was plus 5. And eventually we get to the point where we drop T. And at this point, we also learn something about T. And this is the other half of the prophetic model, is that we get a resolution of our prophecy. We resolve the prophecy, we fulfill it, all the fun metaphorical terms. But the crucial thing is that when we're releasing T, we know that we're at the final value of T, right? We're done with T. So whatever value is in T must necessarily be its final value. And so this construct assume adds a hypothesis to our reasoning context, right? It tells us, okay, from this point on, you know that T.now is T.fin. The prophecy has been achieved. And so from that, we can easily conclude that X must be 5 afterwards in this assertion. And why is that? It's because we know that before we assigned to X the prophecy, T.fin, and we just learned that T.fin is T.now, and we know that T.now is 0 plus 5, and so we now know that X is 5. So are there any questions about this so far? Because it's not surprising for it to be a little bit magical at first. But the interesting thing is that this approach actually captures the notion of borrowing in Rust quite thoroughly. And so the prophetic approach actually can handle pretty much every form, every pattern we have for borrowing in Rust today, whether it's things like splitting borrows in two. So we can, of course, if we have a borrow and a pair in Rust, we're allowed to take out borrows on the fields of pair or of a struct or of any type in general. And in the prophetic model, we can handle that quite naturally by just creating borrows on the subcomponents and just resolving the previous prophecy to be the pair of the new ones or the struct of the new ones or whatever. Similarly, we can handle things like reborrowing, where we take a borrow and we shorten its lifetime by basically nesting a borrow inside of the previous one. And that's exactly what we do with our prophecies. So we just create a new prophecy and we sort of nest it, right? We create a new prophecy A for A here, and we just resolve the current, we say that the current value of the old borrow is the final value of the new one, which is sort of, which corresponds very nicely to that idea of nesting the borrows inside of each other. And then finally, we can also handle operations like weakening, where we forget that we have a mutable borrow, we turn it into an immutable borrow. And the way we handle that is just by saying, well, we've reached the final value. If we're no longer mutating this borrow, then we know we're done with it. We can just assume that we've reached its final value. So the original RustHorn paper provided a syntactic proof of this encoding. Work I worked also on a different encoding of the proof. But even then, it remains a long, tedious paper proof with a lot of edge cases. And though we had a certain intuitive sense that it would be correct, that's not very satisfying for someone working on formal methods tools. So we collaborated, my advisor and I collaborated with Yusuke Matsushita and Derek Dreyer at the MPI on a mechanized version of this proof, which we called RustHornBelt. This proof is an extension of the previous work on RustBelt, which was a formalization of the Rust type system. And it extends it to then be able to reason about functional correctness by embedding these prophecies into the proof. And it also allows us at the same time to actually handle some forms of integer mutability and more complex types that are implemented using unsafe code. So where we sort of break the Rust type system invariant for a little bit, like things like vector. And incidentally, we recently found out that our paper on this work was conditionally accepted to PLDI this year. So if you're interested, you'll be able to read about it in detail soon. But in the meantime, I'll give you a little bit of an overview of how this work actually goes through. So, what is RustBelt? RustBelt was an effort to actually formalize the Rust type system in the separation logic iris. For those who aren't familiar with iris, it's a higher order separation logic embedded in Coq. So you can actually prove your programs, your separation logic theorems in Coq using tactics, and it has a very, very rich and powerful logic that allows you to express a ton of different properties and is very modular. So you can actually develop new notions of resources to model different things, which is something we actually used in our proof. But in particular, so RustBelt formalizes the Rust type system, and in particular, of course, proves the safety of the Rust type system. That is to say that a well-typed Rust program doesn't observe undefined behaviors. And it does this using a technique of semantic typing. The idea being that typing rules are actually theorems in RustBelt, and so you can always prove new typing rules which correspond to types that are implemented using unsafe code. And so you can prove new typing rules, and so you can extend the type system with new fundamental sort of types like vector. And so this is a very flexible framework which gives a very good accounting of safe encapsulations of unsafe code. But it's limited purely to type safety. And so in our work, RustHornBelt, we extended this work to be able to reason about functional correctness by turning type judgments in RustBelt into what we call type spec judgments. The idea being we also associate, instead of just associating a type to an expression, we also associate a weakest precondition transformer representing the specification of that specific instruction, expression, or function. Doing this required a lot of technical work. So in particular, we had to develop a different way of representing and reasoning about our prophecies. And we had to do a lot of work on actually extending the sort of logical machinery, the logical relation underlying RustBelt to handle having relating types and preconditions to every instruction. But in the end, what we ended up with was a judgment that looks something like this. So we'll break it down in just a second. On the left-hand side, we have our input context. So we have our lifetime context and our type context. The lifetime context, of course, is used to talk about whatever lifetimes we have for borrows that are currently in scope. Whereas our type context is used in the standard sort of typing way, right? In the middle, we have an instruction. So this represents sort of an atomic step in the program. So it's something like addition, multiplication, creating a borrow, dereferencing a borrow, writing to borrow, these kinds of things. And then on the right-hand side, we have our output context. So because we're talking about verifying an imperative program here, and because of some specific technical choices in RustBelt, all of our instructions sort of are mappings from inputs to outputs. So we always produce an output context from an instruction. So it basically says, what is the state of the memory after we do this instruction? So for example, if we created a borrow, the output context would have this new borrow inside of it. So the output context is structured in the same way as the input context. And then at the very end, we add this specification. So the specification just says, well, what actually happens when you evaluate I? What is the precondition that you need to be able to evaluate I? More specifically. So here's we have some example judgments here. Some of probably the key ones. So we have our very first one, which is probably the most important judgment for RustHornBelt, which is being able to actually create a mutable borrow. So how does this work? We start off with some value. In RustHornBelt, we always box all of our values as it simplifies the proof. So instead of, you can read the box T here as just being something of type T, but yeah. So we have some value A of type box T. We borrow A, and we produce some value, which we call B here. We have a little binder for B, which is going to be of type mutable borrow of T. But we also have A, of course, which is frozen for the lifetime of the borrow. So that means we still have A in our context. We're just not allowed to use it until we're done with our borrow. And what specification do we actually associate with all of this? Well, as I said before, we write our specifications in weakest precondition form. So it's a little bit particular. But the idea here is we have psi, which is a binder for the post condition. So we say, okay, given a post condition and given A at the start, this is the little brackets A, we're going to apply to the post condition A prime, which is our prophecy for the borrow, and the pair A prime. So we're going to basically, what we're doing here is we're mapping, the post condition is going to take as inputs, the post condition is going to take as inputs the values of the output context. So it's going to take something that represents the A here, something that represents the borrow B here. And what values are we going to give it? We're going to give it the prophecy for our borrow, along with the pair of that represents the actual borrow, so the current value and its prophecy. Similarly, we can give the typing rules for writing and for releasing a mutable borrow. But I think it'll be a little bit more clear when we look at some actual examples later on. Right, so all this, hopefully, I know it went a bit fast, but hopefully you got some intuition for how prophecies actually function for verification. But this is all the underlying mechanism behind Creusot's handling of mutable borrows, and a little bit of a little overview of the work we did on actually shoring up those foundations through RustHornBelt. Now, Creusot, on the other hand, is an actual tool that's built on this technique, capable of verifying relatively complex code in Rust. In particular, though, it means because we're based on this prophetic technique, we only attempt to verify safe Rust code, right? So we don't make any efforts to verify unsafe code. And our current sort of approach to that is to say, if you want to verify unsafe code, you're better off doing it in calc by hand and then proving a safe interface, and then just abstracting the unsafe code away in Creusot. I'm sorry, there's somebody who is not muted. If you could make sure to mute yourself, please. Oops, sorry. And then in particular, Creusot adds quite a lot on top of this prophetic encoding. So in particular, we've developed a specification language for our Rust programs, which allows us to actually describe the properties that we want to verify in a fairly ergonomic way, and is built on top of Y3, which is a platform that abstracts over quite a few S&T solvers, and also provides a whole bunch of mechanisms to aid in verification, which gives us, in the end, a very efficient, or at least in my totally unbiased opinion, a very efficient platform for developing a verification tool. As I said, Creusot provides a specification language, and if we actually want to specify, if we want to verify Rust programs or verify programs at all, we need to be able to actually say what we want to verify. And so we call the specification language Pearlite, which is a microstructure in steel. So we're keeping the metallurgical trends. Perlite is a standard sort of behavioral specification language, in the sense that we specify behavior of Rust functions using contracts. So we have our standard kind of clauses, requires and ensures. Those contracts then are composed of predicates or propositions, which are basic. We have all sorts of basic expressions. We have arithmetic comparisons, if else, function calls, all that fun stuff. And then we, of course, have a bunch of standard connectives that we would find in a specification language. So we have the ability to write implications, to write conjunctions, to write disjunctions. We also have quantifiers. Perlite may look, as you'll see on the next slide, Perlite may look a lot like Rust code, but is really quite different, right? We actually have ability to talk about things which can't be executed because we're just writing essentially mathematical formulas. And similarly, we also have access to mathematical data types. So we, for example, in Pearlite have the type sequence T, which represents a mathematical sequence of values T. So this is much, in a lot of ways, is like a vector, but is of unbounded length, where T is any value. And of course, it also doesn't correspond to a slab of memory that has, n values of type T inside of it. And then we also have things like the mathematical integers. But then in Pearlite, we have one key operator, which is quite different from other languages, which is most similar to Prusty's pledge. It's the final operator. And this is how we actually reason about the behavior of mutable borrows in our specifications. So we actually allow you to talk about the final value of a borrow in a specification directly. And this allows us to say all sorts of complex things about the behaviors of our programs when they're mutating pointers in a fairly concise manner. So how does this all fit together? So if we have a little function here, increment, all we do is we take a mutable borrow of x, right, over some pointer, some integer, sorry, some unsigned integer. And all we want to do is we want to increment that pointer by 5, right? We want to increment our borrow by 5. So how do we specify this behavior? What we would like to say is that, well, after we call incr with whatever value for x, the value that's inside of x is going to be whatever was there before plus 5. And the way we do that in Pearlite is like this. So what we say here is the final value of x is the same thing as the initial value, which we refer to by using star, the standard dereferencing symbol in Rust, plus 5. And this makes sense here because when we called our function incr, right, we gave it x. So whatever is inside of x is the lifetime is going to end at the end of our call, right? So we actually, it makes sense in a lot of ways to refer to the final value of x here because it stays inside of our function. But this actually is also perfectly extendable to the case where we're returning a borrow. So for example, here we have a function where we take 2 borrows, right? We take a borrow A and a borrow B. And we also take a Boolean toggle, and based on that Boolean, we're going to return one of the 2 borrows. So how would we actually specify this? As I said before, in Pearlite we have standard sugar, so we have things like if expressions, and so what we're going to say is, well, if toggle is true, right, we're going to return A. So the result of the function is going to be A, and here the result is the borrow. So it's A. It's everything about A. We're not just saying the current value being pointed to by the result is the current value of A. We're saying the result is the pointer A, right, the borrow A. But we're also saying something else. We're saying hat B equals star B. And so what we're saying here is we're saying the final value of B is equal to its current value, the value it had at the entrance to the function. And this is because once we've called proj toggle, we're throwing away B in the case where we return A, right? So we know that B is never going to be mutated, right? So we learned at that same time that we return A, we actually also learned something about the value in B. As a side note, I realize I didn't say this before, but in Pearlite, we also have this triple equals, which is yeah. Okay. Yeah. So there are 2 questions talking about the previous example where we had an increment about the handling of overflows, and you're both correct in pointing that out. And as it is today, Creusot checks overflows systematically. So the specification I gave would actually be wrong. We would, if we tried to run this example through Creusot, it would complain telling us that, well, what happens if X is about to overflow? But yeah, yeah. So we would have to require that X is at least 5 less than the max value of U32s. In general, how do we handle runtime panics? In general, Creusot verifying if a program passes with Creusot, there should be no runtime panics at all. So the default the default conditions that are generated by Creusot are going to guarantee the safety of your program. So panic freedom. Yeah. Right. And so as I was saying, in one case, we return the borrow A, and in the other case, and as a result, we resolve the borrow B. We learn that the borrow B will no longer change. And in the other case, we get the sort of symmetrical property about the other borrow. And so in Creusot, I mean, I won't bore you with necessarily with this example. We're about to see we're about to have a little demo of some other code, but we can give a specification to the previous list reversal example that we saw earlier on. And so here, what we would like to say is that when we send a linked list into our reversal function, after we call reversal, the linked list that we have is reversed, right? And so the way we express that property at the top level is by saying the final value of L, our list, the final value of L is going to be the rev append of the initial value, the current value of L, and nil. And we use this function rev append, which the functional programmers among us may recognize, which basically does what it says. It reverses and appends two linked lists together. But it's more convenient to express it in this manner for the proof, because then our loop invariant is quite trivial. Our loop invariant just says, when we rev append the head, which is what has already been reversed, and the previous list, which has already been reversed, and the head, which is what remains to be reversed, it's the same thing as reversing the entire list, right? And so using this, we can prove that our list reversal is not only safe memory-wise, but actually does reverse our list. Right. I'm going to skip over the traits section, I think, because that way we'll actually have time for a demo. But we can actually support traits in Creusot, but I wanted to actually have a chance to do a demo for once. And so if you'll bear with me for just 1 second, I'll switch over to the other windows to show you how these work. All right. So, can everybody see the screen? So here we have a simple little binary search on a vector of integers. The algorithm is pretty much the one used in the Rust standard library. But instead of being over a slice of integers, we do it over a vector of integers, because at the time Creusot didn't support slices. So what happens when we feed it? I'm sorry, I'm going to share my entire desktop, because that way I can actually show you what happens when we feed it through Creusot. When we feed it through Creusot, right? So we have. Is this big enough, or should I make things bigger? So if we have our little binary search here, right, we can build Creusot. We can build Creusot and run it on the file. And Creusot is going to generate this massive file in a format we call MLCFG, which is the input format that we use in Y3. It's a functional language where we've used this prophetic encoding to sort of eliminate all of our issues with mutable borrows. So we've generated this file, and we can now open it using Y3's existing proof IDE. We get this file, we get this view over here. And I'm sorry, but the chat window has disappeared now that I'm sharing my entire screen. So if you have a question, please don't hesitate to let me know, but I don't know if I can. Oh, okay, there we go. So we generate this file, we load it up into Y3, and we can see on the left-hand side, we can see these two icons here, which represent proof obligations that remain to actually be fulfilled. So we can run standard tactics in Y3. So Y3 has support for a form of tactics called transformations. These are, as they sound, they will take a proof obligation, they will take a verification condition, and they will apply certain logical rules to it to hopefully simplify it. And we can also throw SMT solvers at it. So in this case, this obligation turned out to be very trivial. And so the SMT solvers handled it without issue. And then, of course, Y3 will then generate the proof obligations that correspond to our binary search function. And we throw the SMT solvers at it, and they're not happy. They time out. And so we can attempt to simplify things a bit. So we run this split tactic. And it takes our original big proof obligation for binary search and breaks it up and hopefully labels each condition for us, right? So we can see, okay, well, here we have a precondition on this function index. We have an integer, we have to check for an integer overflow here. We have a bunch of checks, and we can run the provers on it. We can see they can handle a lot of the integer overflow, a lot of these kinds of basic conditions, but they're not able to handle everything. And that makes sense. So for example, we can take a look here. We can see, okay, well, here, what is asking us to prove a precondition for index. And in Y3, if we switch to the task view, we can actually see sort of what's being asked in the logic to be proved. And so we're being asked to show what corresponds here to showing that the index is less than the length of the vector. So we're going to have to go back and actually instrument our program with the specification to allow the provers to conclude that everything is all right. Some of you, as well as you may have noticed from this demo, Creusot doesn't actually allow you today to verify code using Rust syntax in the proof interface. This isn't a fundamental limitation, it's just an engineering one. There's a lot of things to do and only so much time to do them. And so it is something I would very much like to work on actually being able to have an interface that's as nice as a tool like Prusty, where you can actually see your Rust code and see the proof obligations directly on your Rust code. But only so many hours in a day. So if we go back to our example here, we have a few issues. So the first thing is we actually know nothing about our value of LM here. We also know nothing about our array. So if we want to actually be able to do a binary search, we need the array to actually be sorted. So the question is, how many people are working full-time equivalent on Creusot? Just one, me. It's the subject of my thesis. So of course my advisors are helping me out, especially on a sort of theoretical and design level. But in terms of implementation, it's just me. It's all open source, it's all on GitHub, but you know, everybody has their own projects. So so for our binary search to actually succeed, we need to give it some more information. And so above here, you can see that I've defined a couple specification functions. So these are marked with this attribute predicate, which designates them as being in Pearlite. So these functions are not actually Rust functions. You can't call them in a Rust program. They won't exist in your Rust program, but you can call them in your specifications. And so what we can say here is we can add a little precondition. And we say, well, what do we say? We're going to require our array to be sorted. Well, actually, right, so it's actually going to be sorted. And we actually have to use this little symbol here, which allows us, it's a syntactic sugar for what we call model, which is a trait in Rust or in Creusot, which talks about the representation of a value in the logic. So we represent vectors by sequences of values. And so what we say here is we say the representation of our vector R is sorted. So we're saying our vector is going to be sorted. And we're also going to say something else. We're also going to say that LM, we're going to say LM is less than we're going to say that our element is within the bounds of our vector, right? The value of our element is less than the length of our vector. And so now when we run everything through here, this time, I should have saved the session. If I'd saved the session, we would see all of our previous goals and which ones had changed. But we should have made a little bit of progress here normally. Right, okay, yeah. So we did make a little progress, but what's happening here is that if we looked at our little example, we still have this loop here. And we need to show, what we're being asked to show here is that the midpoint is still within the bounds of our vector. And so I'm going to cheat a little bit because I have the actual answer right here. And so I'm just going to go ahead and copy this invariant here. And we're going to see basically that will solve this thing. And when we run it through this time, now we should actually get our precondition satisfied. Boom. We split. So what I did here was I just I did the same tactic as before. I split everything and I ran the SMT solvers on each resulting goal, and they tell us everything is fine. And so with this, we've managed to prove at the very least that our function is not going to crash, right? So we're not going to panic when we're indexing our vector because all of our indexes are inbound, and we're not going to panic when we overflow integers because we're not going to overflow. We don't actually say anything about the functional correctness of our binary search here. We don't say that we're actually binary searching, but we, if I could just show you, there we go. In this tab over here, I have a version where we've actually instrumented it with the complete specification for a binary search. So in particular, we state that when we return OK, then whatever index we returned inside the OK has the value of our element. Oh, wait, yeah. So Daniel asked a question of saying that not all loops in Rust are explicit. How would you attach an invariant to an operation that maps or folds over an item? So right, so we in Rust, of course, we have the ability we have while loops, we have the loop construct, but we also can write looping code by recursion, and we can of course use iterators and do all sorts of crazy stuff on them to effectively hide our loops from the source code. So recursion, for example, is not an issue because each recursive call we're required to prove a precondition and we're guaranteed the postconditions, and that using that you can you end up encoding your loop invariants in the contract. So recursion doesn't cause an issue, but on the other hand, iterators do, and we're actually going through work right now on handling iterators. But the real challenge with iterators is that in Rust, they're written using closures, which can do a lot of complex stuff. In particular, closures can capture values mutably and mutate those. So for example, you could have, you could map over an iterator and count how many times you've mapped. And so that's quite complex to be able to reason about. We think that we have some good solutions to those issues, but they're not yet ready to really share. But yeah, I mean, in practice, at the very least, all loops that are the loops you construct in your CFG are going to be through while and loop constructs in Rust, though. Did that answer your question? All right. Right. So right. So with this example, if we ran the binary search code, sorry, there we go. I just demo. If we ran Creusot on the fully annotated version, we get a similar result as to what we just saw, except with a lot more proof obligations here if we break everything down individually, because we gave it a bunch of specs, which are going to generate a bunch of corresponding proof obligations. But we can run Z3 and CVC4 on it, and they're quite happy to tell us rather quickly that our binary search is correct. So in Creusot, we've applied this we have a growing set of test cases, but perhaps one of the more interesting cases that we've applied this is there are certain programs which have been used as benchmarks of difficult programs for C verification, because they make, in C, we have a bunch of obligations that appear around separation logic, but that with Rust ownership typing end up being trivial. And so an example of this is here. Sparse array. In this sparse array example, where it's an implementation, it was originally published as a set of benchmarks in a paper on a tool called VACID0. But the idea here is that we implement a sparse array as a set of vectors, basically, tracking little chunks in our array. And typically in C, we'd end up proving a bunch of issues about whether or not those vectors are actually separated, whether or not the pointers in our vectors are separated, and other issues. Whereas by encoding things into Creusot, all these difficulties sort of evaporate thanks to Rust type system. All right. I think, what are the main benefits? Okay, so the main benefits of using the prophetic model in Creusot. The question was, what are the main benefits of using a prophecy model in Creusot? And I think there's two aspects to it. The first one is performance, performance and flexibility. Prophecies allow for very, very performant verification of code. So far, I mean, our most complex examples, even something like verifying a solver for the knapsack problem for the 0-1 knapsack runs in something like 5 seconds on a single machine. And this is far from a trivial proof in the end. So the prophetic model is very nice because it somehow captures, the encoding somehow separates the sort of spatial aspect, the sort of structure of your heap, from what's inside of it, and the sort of functional aspect. So we get to eliminate all that stuff about, memory and heap structure and memory models, and focus just on sort of the fragment that corresponds to the behavior of your program. And the second thing is it just maps very naturally onto Rust, right? So this prophetic model, it encapsulates all the patterns that we have for borrowing today very naturally. So there's no specific effort to support splitting or reborrowing or unnesting or all sorts of crazy operations we can do with borrows. It just occurs naturally. Yeah, I mean, to me, those are the two big aspects to the prophetic model as it exists. And then Rod Chapman had a question about whether or not we had examples of verifications of cryptographic algorithms. No, we don't have examples of verification for cryptographic algorithms, but that's more due to me not knowing about cryptography. I know that there's been a little bit of interest, there's been some interest by people who do cryptographic verification with using Creusot for cryptographic algorithms. And I would be quite interested if somebody actually knows interesting algorithms to verify. I would be interested in taking a look at that. I don't see any reason that Creusot couldn't be used for that. It's just a case of I don't have expertise in the domain. All right, are there any further questions? Well, if not, I think we can wrap things up. It went by a lot faster than I thought. Oh, sorry. Yeah, there's okay, so Pointer Bender has a question for what does the roadmap for Creusot currently look like? Right now, we're actively working on closures and iterators. I think we're sort of coming up to wrapping that up in the coming weeks, at the very least, the sort of initial version with the fairly complete support, I would like to say. I think then in terms of big features, probably the next big feature that we're looking at is going to be type invariance. So the ability to actually ensure, I mean, as the name implies, that values of specific types satisfy an invariant at all moments. I think there's some interesting code that we can actually write with that. And then I think what we really want to do is start growing the standard library that Creusot ships with. So Creusot comes along with the standard library of specifications, so we can actually attach specifications to functions from the standard library, and we have for a certain number of them, but we'd like to really start growing that out into being able to really use a large portion of core library types and functions, and actually applying it to larger scale verification. Yeah. So then there was a follow-up about type invariance and whether or not they could be emulated using requires, ensures, and predicate annotations. They absolutely can. And there is a master's student who's working on his master's thesis verifying a SAT solver using Creusot, who I believe is here, Sarek. Sarek Skotam, who has been forced to use this, much to his frustration, I think. But it's still something that we would really like to improve, and I think that there's it really does change the ergonomics of verification to have that built in. All right, if there are no further questions, I think we can wrap things up for tonight. I hope that you got something out of this. And we'll see each other in a month for a presentation on, correct me if I'm wrong, Connie. I know I always get the name wrong, but the model checker being developed at Amazon. All right, bye.